Hello and good morning, everyone. Imagine if it were possible to design ultra-tough thin-walled structures with ultimate fracture toughness and yet much lighter, and this without any change of the chemistry or inventing a new microstructure. My name is Negar Mohtadifar. I'm a first-year PhD student at UC Louvain, and today, I'm going to explain how we have taken the first steps towards making this possible by understanding the thickness dependence of fracture toughness. So in thin plates, and when I say thin plate, I mean when the size of the plastic zone in the crack front is smaller than the plate thickness, the fracture toughness is not actually intrinsic, and it is changing with thickness. As you can see in this figure, in materials with large strain hardening exponents, as you decrease the thickness, the fracture toughness starts to increase. It reaches a peak value at a specific thickness, and then it starts to decrease. But we don't know what is controlling the peak value, the corresponding thickness, and also the plane stress fracture toughness. And so in the team that I'm working with, me and my colleagues are trying to find what are the controlling factors of resistance to fracture, including thickness. So in order to determine the fracture toughness, we chose double-edge notch tension specimens. And these specimens allow you to benefit from the essential work of fracture concepts, which allows the separation of the work spent in the diffuse plastic zone from the work of necking and damage in the fracture process zone. To briefly explain it for the people who are not familiar with it, depending on the ligament size between the two notches of the specimen, you can have different regimes in which we are interested in essential work of fracture. We are interested in the plane stress one. So if you design similar specimens with the constant thickness, and increase the ligament length within a valid range, and then determine the the specific work of fracture and plot it against the ligament length, do a linear regression, you can separate the essential work of fracture from the work spent in the plastic zone. And if you repeat this for different thicknesses of your specimens, and again, plot your essential work of fractures against the thicknesses, do another linear regression, you can extract the pure work of damage from the work of necking indicated by sigma n. We also extracted other fracture toughness indicators, including the essential work of fracture at crack initiation. And it is similar to essential work of fracture method. We also measured the critical crack tip opening displacement, we followed the methodology proposed in 2000. And we measured it with two different methods, polishing and tomography based. And this was done on interrupted tests of at different advancements of cracked. And we also calculated the J integral value by the formulation proposed by Jim Rice. So the material that we were dealing with is stainless steel 316L. It has a large strain hardening exponent. We had a plate of thickness 7.85. We extracted our dense specimens along the rolling direction with the dimensions that you can see in the picture. with 3 different thicknesses, 1.5, 3.7, and 7.85. And so after testing, it was important to verify that the ligament lengths that we chose were valid for the essential work of fracture. So first, we make sure that at the initiation of the crack, the ligament length is fully plastified. And secondly, for each of the thickness, if we plot the normalized force displacement curves for each thickness, you can and superimpose them. It means if they superimpose, it means that the mechanisms in play are similar for the specimens. So we check this. And finally, based on the methodology that I explained, we extracted the essential work of fracture for different thicknesses and plotted them against the thickness. As you can see in the curve indicated in blue, we obtained the plane stress essential work of fracture, and comparing it to the results in the literature, they were quite similar. However, the work of necking was different. We did the same thing for the EWF initiation. And finally, we compared the EWF with EWF initiation and the J integral values. And as you can see, the J Rice values are close to the initiation values of essential work of fracture. And the difference that you see between the essential work of fracture and the J values is due to the it reflects the extra energy dissipated due to the crack propagation. Finally, we did interrupted tests to measure the critical CTOD. First, we observed the crack tunneling as the crack advanced. You can see the tearing versus the positioning along the thickness, and you can see a clear tunneling. And also this initiation-based fracture toughness indicator showed that fracture toughness is indeed thickness dependent. And finally, I would like to mention that in the group that I'm working with, parallel to my experimental work, there is a modeling team who have developed a non-local ductal fracture model. And they have conducted simulations on dense specimens with different ligament lengths, and they were able to extract the essential work of fracture and show the thickness dependency of it. And with this, I would like to summarize my talk. We conducted fully fractured and interrupted dense specimen experiments, and we were able to extract different fracture toughness indicators and show that indeed fracture toughness is thickness dependent. And for the future work, we are planning to have a better look at the necking and the crack tip and compare it to the models, semi-analytical models in the literature. And also, again, I would like to connect my experiments to the FE models and gain a better understanding of the controlling parameters. This would bring my talk to an end. Thank you for your attention, and I'm open for your questions.